Okay, let's talk about what plot is right for you. How do you know if you're using the right plot, or how do you know which one to choose? Well, first of all, there is no right visualization. Second of all, not all plots are created equal. And third, what do you want the chart to say or do? Are you looking at distributions, change over time, relationships, single variable, multiple variables? You have data. There are certain things you can do with the data. Is it continuous, numeric, categorical, spatial? What question or relationship are you trying to illuminate or communicate? Sometimes it's exploratory. You're looking for patterns, and sometimes it's explanatory and you're trying to communicate a specific message. So what do you want to know? What do you want to see? We can create charts to look at how values are distributed, compare groups, examine relationships between variables, assess how parts comprise the whole, and identify trends over time. And there are certainly other plots out there that do other things. Let's just talk about some of these basics. What if we want to understand the distribution? Like, what is the range of values in my sample? Are the data distributed the same way this time as they were last time? Are there any unusual points that I should investigate? Whether you look at a histogram or a bar chart, you will see ranges of values and distributions. The charts all have different kinds of visual strengths. This is a variation on a histogram, showing the frequency of elements that appear in Bob Ross's paintings. The categories overlap, at least one tree, at least two trees, and then tree types have their own category, which is not very good science, but it's still a fun example. Bridges and cliffs down here on the bottom are apparently not Bob's thing. Let me say here that I hope you will stop these videos and take the time to read these charts at your own pace. There is a lot to take in, and I'm not going to build in awkward silences into the narrative to give you time to answer my rhetorical questions and give you time to read the axes labels and stuff. But I really hope that you will pause and give these plots your time and attention when you can. Okay, so moving on, distributions. Histograms, we talked about these in other videos. Remember that they look a lot like bar charts, but they read differently. The baseline is continuous data put into classes or bins instead of discrete categories. These allow us to see how data are distributed. Because histograms group numbers into these bins or classes, those ranges are very important. So let's talk about those really quick. This is a set of histograms looking at the age distribution of Titanic passengers. The ages range from 0 to 71, and you can see there are a lot of passengers that were in their 20s. Histograms depend on the chosen bin width. The first, upper left, has a bin for every single year. The second one, upper right, clusters by 3-year classes or bins or periods. Lower left has classes of 5 years and 15 years in the lower right. To show the important trends in age distribution of the Titanic passengers, we can probably agree that the bin width of 1 year is too small. There's a lot of chatter. The bin width of 15 years is too large and oversimplifies, and we lose the information, this kind of bimodality about the number of children that were under 5. Both of the bin widths of 3 to 5 years work well. We maintain that slight bimodality here, and we see this second group, and they don't oversimplify. So bin width, class size is very important. Distributions, we also need to talk about how we describe what these distributions look like. So again, for a review, normal distributions are bell curves. If you shift the peak to the right or the left, it becomes a skewed distribution. A right skew means there's a tail off to the right side. Bimodal distributions are composed of 2 peaks or 2 groups. And basically just lets you know that you have, 2 different things going on within the data set. Okay, histograms can also show us frequency of observations. This chart shows wildfire size in hectare on the X and frequency on the Y for 2 different simulations of wildfires. two different treatment scenarios. The darker bars are treated, a scenario where the land was treated, and then the land was untreated for the gray bars. We're able to compare and see that the fire size for the treated scenarios are overall smaller, with a smaller tail off to the right and a higher frequency of small fires than in the untreated scenario. I hope that makes sense. That's an important thing to be able to do with these histograms. Okay, do you want to compare groups? This is your classic bar chart, categorical data on the X and value associated with each on the Y. Here, it's a nominal comparison, north, south, east, west. There's no particular order to these. You certainly could rank these. Here's a ranked comparison. Notice how much easier it is to draw attention to the order that these are in. So if you need to maintain some sort of geographic order for some reason, like with north, south, east, west, that's fine. But ranking them does make the information a little bit, kind of remove one step by putting them in an order. So this is the percentage of the population that attends different cultural events. Still comparing groups. Another way to compare groups is by looking at distributions. We talked about box and whiskers before. This is pre-box and whisker calculation. This is just the observations. We've got miles per gallon on the Y and cylinders, the number of cylinders on the X. And you can see that because it's categorical data, we have a lot of observations in each category. So this helps us focus on high and low values, relative distributions, the density of the observations, right? We can look for similarities and differences between the groups and look for change over time if this were time instead of something like cylinders. So what can we do with this to make these observations more readable? Do you have any ideas for how we could unblock these and see these? Well, one way would be to create a box and whisker plot, of course. We can also do things like jitter the data. This is called a jitter plot. I think I messed up my animations here. This second one's called a violin plot. It's basically a histogram smoothed out and then tipped and created into a mirror image of itself. The jitter plot, this is kind of interesting. For each month, we've got the temperature, and each observation point is a day during that month. We don't know where this is, but it's a way of spreading that out so you don't get this cluster. You could also make these points bigger, right, and make them semi-transparent so that we get an intensity of color where there's a lot of overlap. This is called a ridgeline plot. The ridgeline plot, oh, there's my other labels. The ridgeline plot is like a histogram, just not violin, basically. So lots of things we could do with those individual observations so that they're not stacking up on top of each other. Okay, do you want to examine relationships between variables? Here's your classic scatter plot again. This is comparing per capita CO2 emissions and gross national income. Very similar to the Gapminder data that we looked at and the Our World in Data plots that we looked at, where we're encoding size, or I should say population with size, region by color, and then so this is 4 variables altogether. And notice how effective the annotations are, the labels, adding things in like global means and things like that. Really small touches that add a lot of information to plots like this. Okay, just a slight deviation, refresher. Remember that we can describe relationships in scatter plots as having perfect positive correlations, high and low positive correlations, and then negative correlations. And then remember that the R squared is the measure of how close the data are to the fitted regression line. Again, this should be kind of in your quiver at this point, and if you need to, please check whatever resources you have or need to get a refresher on these kind of statistical things that are prerequisite. Okay, so assessing parts to the whole. Here's our classic pie chart visualization. Again, these are okay despite what many people would say, as long as you keep it simple. It is sometimes the easiest way to show very simple data sets. The circle represents the whole, the slices are the proportions of each component or variable. You can label them with the percent or the raw numbers, but you should know that there are options to the pie chart. One is called the waffle chart. There are 100 squares. Each one represents a percent. They're colored to represent the fraction of each part. And I'm going to show you some other examples of this later. They're helpful for showing change over time, I think, not necessarily the easiest way to show this data. Another way to show this same kind of data is with a tree map. You know, again, you could be, I'm just going to jump ahead a little bit about how humans see. It turns out it's not very easy for humans to register the differences between these angles, which is what we're doing when we read a pie chart. We can read kind of the relative areas, the relative arc lengths, or these angles. That's what we're doing. We're comparing those three things when we look at a pie chart to try and determine which one is bigger. When we look at a tree map, we have to do the same thing. We have to gauge the lengths of the sides to calculate intuitively the area of the rectangles. It turns out humans are better at doing this than they are at doing this. And you can agree or disagree, but we're going to talk about some studies that have been done that rank the human ability to accurately decode some of these visual strategies. Anyway, just another option. Tree maps. Another less obvious and not necessarily always an effective way to show parts to a whole are stacked bar charts. This is not a good way to do it. What we're looking at here are sales by category, like phones, chairs, binders, bookcases. The colors represent the geographic sales district. Instead of showing the dollar amount or the total sales, you could sum the sales and calculate the percent of total sales for each category. You could do that. Another way to show the data would be to show, like for example, of the total phone sales, which district is performing the best. And that's what's being shown here. Here you can see that it's really easy to compare and see that the West is outselling tables, but it's not performing well in machines. It's relatively easy to see that the East and the South are selling the bulk of machines, but it's not easy to track sales for the East and the South individually. And we talked about this before. It's because our eyes need a consistent baseline to compare against in order to kind of decode or register the individual lengths of those bars. And we lose that consistent baseline for the interior sections. We're going to talk more about this later, but it is much easier to kind of track the East and the South, especially when they're not highlighted. When they're highlighted, it's a little bit easier, but without a consistent baseline, that's really hard to do. Okay, part to whole comparisons. We talked about frequency distributions and probabilities. As long as they sum to 1, this is another way of showing parts to whole. But it does take a little bit more savvy reader to realize that frequency or probability charts, when shown in fractions like this, should sum to 1. Okay, so remember how I said that you really need to pay attention and carefully read charts. Sometimes they don't deserve your time and attention. So this chart is showing change over time between parts to a whole. In this case, the fractions are different types of mistakes made Monday through Friday. Yellow is product-based mistakes, red are pricing mistakes, etc. So what if your task was to learn what type of mistake was most common and when it was happening so you could address the problem? Where would you start? If you were me, you'd be lost. You'd look at this and you'd be like, yeah, forget it. Whoever organized this and did it like this, forget it, they're fired. Edward Tufte, I've mentioned him before, he is quoted as saying, and I'm going to paraphrase here, the only thing worse than a pie chart is several pie charts. The viewer is having to compare really awkward quantities that are spatially disarrayed within the pie and between the pie. And the fact that they're stacked horizontally and vertically is just horrible. This is terrible. He also complains that they are very poor in data density. You will learn that Edward Tufte believes, this is a little foreshadowing to an assignment that's coming on down the road. He thinks that the pie chart should be abolished. I don't take that firm a stance. I do feel that way about north arrows, but I don't feel that way about pie charts. Okay, moving on. Talking about trends over time. The classic is a line chart. Line plots typically have time on the x-axis. You really can't connect things together unless theoretically something's happening between the known locations. Okay, let me back up. Okay, so the line creates a connection between data points. If you have measured values in 2001 and another measured value in 2003, the line is going to be straight between them. We could measure values between those times, so the line is a generalization, but it's also an appropriate way to connect the two data points. But know that the chart can't say more than what is there, if you follow me. We can't make assumptions about, for example, if you look at the dissatisfied line down here, between 2013 and 2014, there's this uptick. That's all we know, that from this point to this point, there was an increase in the number of people that want less strict gun laws. But we can't make any assumptions about what's going on during the year 2013. It's just a generalization. We have data here and we have data here. But like I was starting to say, you can only connect with a line things that are theoretically connectable, and dates work. You wouldn't make a line chart, for example, connecting sales in the Northeast region to total sales in the Southwest. There is no theoretical thing happening between those that could be represented by a line. I don't know that I'm doing a very good job of saying that, but connect things that logically can be connected. So, time series plots tend to be line charts, and that works because time is happening between the known locations. So these are good for showing trends and identifying key shifts in data. And remember, I didn't introduce this kind of what this table was about. So again, please stop and take time to familiarize yourself with these things as we move into them. Okay, line plots can have more than one vertical axis. You can have more than one thing on your line plot. Here's a great plot showing the undeniable correlation between the number of letters in the winning word of the Scripps National Spelling Bee and the number of people killed by venomous spiders every year. Remember, correlation is not causation. This is from a website called Spurious Correlations, for those of you who haven't come across it yet. There are hundreds of these hilarious correlation pairs. Okay, so again, time is on the x-axis. On the right axis is reserved the values for the death line, and on the left axis are the number of letters in the winning spelling bee words. Okay, a little side note about line graphs or time series plots. A cumulative chart or a cumulative plot is a common way of plotting, in particular, sales. This is a real thing. The red line looks like sales are great, and if this is all the shareholders got to see, they'd be obviously very pleased. But it's a very misleading way to show data. The blue line shows the actual sales each month, and you can see that sales have been pretty steadily on the decline. So it would take a very savvy chart reader to notice this and to question the messaging if only the red line were being shown. So just be aware. Okay, so comparing change over time. This can take a lot of very elegant forms. This is a beautiful graphic meant to show that women in select European countries are starting families later in life. So each one of these is a set of histograms. Each semi-transparent layer represents a country, and the color, the brown and the green, just reinforce that there's two different time periods. Notice how little information we're given. There's a ton of data here, but not a lot of explanatory text, like there's no labeled axes, none of the countries are labeled, there's no scale. All that we're being directed to focus on is the shift of the peak toward the 30-year-old mark, the black line, for when a woman has her first child. It's this shift in the peak of the histograms that we're being told to focus on. Very elegant data presentation. Okay, this is a heat map. It's just like a raster in every way. Every cell contains one value, and the value is being represented by a color. It's genius. So this is like building a little mini raster. There are two position scales. So we've got time along the x-axis, again, which makes perfect sense, and location is on the y. Neither one is a continuous scale. We can think of time as continuous, but we have one average temperature for each month. So it's not continuous, it's a discrete thing. It's not categorical, but it is discrete. Month is ordered and location is unordered. So when the variable is ordered, like months, then the levels have to be placed in the appropriate order, right? We can't order them according to temperature, for example. If it's unordered, like location, then the order is arbitrary and we can choose any order for the cities that we want. Here, the locations are ordered from coldest in Chicago to overall hottest in Death Valley to generate this graduation of colors. But the cities could have been placed in any order and the figure would have been equally valid. Okay, next, the question still remains, what chart is best for you? And to recap, it depends on your message. When we're exploring data, there's a ton of trial and error that has to go into it. A lot of trial. Experiment, look for patterns, question your logic, know your data, get to know your data. When presenting your message, it's the same thing. You need to experiment, talk to people, get people's advice, critique your work. You're going to see things differently through other people's eyes than you who are so invested and knows the data so well. Okay, here's a chart showing millions of gallons of petroleum stock on the y-axis and change over time, comparing 4 regional groups: the US, Japan, West Germany, that's how old this plot is, and other. Okay, so what can we pull out of this? What can you see? It's fairly easy to see that the US has the largest stock and that the quantity on hand has gradually increased over time. West Germany has the smallest stock and the quantity has remained relatively unchanged over time. Okay, so the main message is the ability to track the individual countries' petroleum stock over time, right? This could also be shown in a line chart because there is something logically being produced or consumed, measured between each date. Here's the exact same data presented in a stacked bar chart. So compare this. What's the easiest message to take away? What's the easiest thing for your eye to do? For me, it's easiest to see how the total quantity of petroleum stock changes over time. The sum of all of these groups over time. That's the easiest because it's easiest for the human eye to detect change in length or height from a consistent baseline. Second, it's probably easiest to just see what's going on in the US because it also has a consistent baseline. Does that make sense? Third, you can kind of see that Japan and West Germany combined have a very small proportion of the petroleum stock because relative, we can see that. We can't really detect what's going on with either one of them over time because we're missing that consistent baseline. So what is the goal of your chart? Choose a type of chart and then make encoding choices that support your message. All right, and sometimes it takes more than one chart. Here's a time series plot. We've got time, 1950 to 2017, and the number of acres burned per year in millions on the y-axis. So this chart is telling us that the number of acres burned is increasing over time. Here's a stacked time series. Great plot. Every row represents a year, and it tracks from January on the left to December on the right. Each bar represents a fire. The height of the bar represents the total area burned. Awesome. This plot's telling us that large fires have become more common over this time period. So as you track down from 1970 to 2017, you see that the number of large fires is increasing. Okay, here's information about wildfires in bar chart form. Bar charts show ranks. They help us compare values like number of acres burned, number of structures lost, dollar amounts. And we can use annotation to point out important details. We can include specific labels that give us exact numbers. And here, hopefully it's obvious that we're also using color and contrast to draw your audience's eye. And don't forget the spatial context. There's nothing like a map to show us spatially what's going on.